think we can start. So welcome everybody. I will remind you that this seminar will be recorded. Today's speaker is Niccolò Tonicello, and the title of his talk is I ordered spectral methods for the simulation of compressible turbulent flows. Okay, so thank you for the introduction. So yeah, my name is Niccolò Tonicello, and today I will present, hopefully briefly, the main results of my PhD thesis on high-order spectral methods for the simulation of compressible turbulent flows. My thesis was funded by the University of Rouen under the supervision of professors Luc Verbisch and Guido Lodato. So, just a second. Okay. High-order simulation of compressible turbulent flows is a very challenging field of computational fluid dynamics, as many different physical and numerical phenomena are simultaneously involved, and it needs to be separately treated in order to provide reliable and accurate information for engineering design processes under extreme conditions, starting from the levels of compressibility, which are directly linked to the natural development of shock waves. These features can be particularly challenging to be numerically treated using high-order methods, and ad hoc shock capturing techniques are needed to keep the simulation stable. The high-order discretization itself can have a huge impact on the overall accuracy and stability of the numerical simulation, in particular for under-resolved flows such as large simulations. And finally, the turbulent nature of the flow itself needs to be taken into account, starting from classical incompressible turbulence modeling till move towards more complex modelizations of compressibility effects. So today's presentation will be essentially organized following these three main topics. The first part will be focused on the shock capturing technique I developed during the first part of my PhD. In the second part, we will discuss about the most common spectral analysis techniques to estimate numerical dissipation and dispersion of high-order methods. And finally, we will consider a series of fully turbulent compressible flows where all the above-mentioned features will be simultaneously involved. So the first part of the presentation will be on the entropy-preserving low dissipative shock capturing developed in the first part of my PhD. It is quite well known that trying to interpolate a discontinuous signal using high-order polynomials gives this arising of oscillations close to discontinuity. This is commonly known as the Gibbs phenomenon. Of course, this can lead to stability issues, in particular if these signals represent physical quantities such as density or pressure. Of course, the oscillation can lead to negative values and to the simulation breakdown. There are essentially two main ways to solve this issue: the use of limiters and use of artificial viscosities. In the case of limiters, the numerical scheme is forced to behave essentially linearly close to the shock wave, so there's a change in the discretization. The numerical scheme is modified in order to deal with shock waves. In artificial viscosity techniques, instead, it's based on the additional terms to smooth out, to regularize shock waves. So there's a change in the equations themselves. In this first part of the presentation, I will compare two different kind of artificial viscosity models, classical Laplacian artificial viscosity, and the newly developed physical artificial viscosity during my PhD. So, in both cases, where you use limiters or artificial viscosities, you always have to distinguish two separate steps, which are first is shock detection, essentially, to identify sharp features, and the second one is to shock regularization, essentially. Within the high-order approximation, with high-order framework, you can use the full polynomial expansion of a given signal and the truncated series to compute a scalar quantity which quantifies the levels of regularity of the signal within the finite element, comparing essentially the L2 energy associated to only the highest, largest mode with the whole expansion. Then using this term, using this scalar quantity, you can define a activation function varying between 0 and 1 to distinguish smoothly were resolved from under-resolved features of the flow field. Of course, the signal C needs to be somehow connected to the compressibility levels. So the usual classical choices are density, pressure, or combination of characteristic functions. characteristic variables. The second part is essentially shock regularization. So we are considering additional terms in the compressible Navier-Stokes equations for the Laplacian artificial viscosity. These are just Laplacian-like terms in the conservative variables, whereas physical artificial viscosity is based on an augmentation of the physical viscosities and diffusivities of the fluid, namely shear viscosity, bulk viscosity, and thermal diffusivity. For this specific model, the artificial shear viscosity is dropped, and the thermal diffusivity is linked with the bulk viscosity using a bulk-based prime number. So the main ingredient of the shock capturing technique is the bulk viscosity, which is a reasonable choice since bulk viscosity is associated to dissipative mechanism due to expansions or compressions of the fluid. And we will see that this is a key point to reduce the dissipation of the shock capturing technique. It is quite well known that the entropy profile across a viscous fluid shock is non-monotonic. There's a peak in the middle of the shock wave. It's a little bit less known that this result can be generalized also in the initial shock limit, where the entropy can be defined not just like an Heaviside function like density, pressure, and all the other variables, but as a sum of Heaviside functions, where the value S star can be obtained a closed formula directly from Euler's equations. The idea is that we want to study how different shock capturing techniques will affect this property, which is intrinsic of Euler's equations themselves. So for we consider as a very first test case a simple one, the shock collision between two identical shock waves of Mach number equal to 5 and 10, so that we are in a quite challenging condition. And we will focus our attention on the shock profile in terms of density, pressure, velocity, just to see that this phenomenon is successfully suppressed, and in terms of non-monotonicity of the entropy profile instead. Moreover, this problem is affected by a numerical artifact known as overheating, which is essentially a persistent increase of temperature in the middle of the domain after the collision between the two shocks. And once again, we want to see how the different schemes will interact with this particular phenomenon. In this sense, here we show the density profile and the entropy profile after the collision of the two shocks, where the solid line is the physical artificial viscosity and the dotted line is the Laplacian artificial viscosity. We can notice that in the middle of the domain, we have this overheating phenomenon, which is an increase of entropy, and so consequent decrease of density in the middle of the domain. But this is present only using the Laplacian artificial viscosity, whereas the physical artificial viscosity gives the correct flat profile in this region. Secondly, if we just observe the density profile, we notice that more or less the two schemes are quite equivalent in terms of regularity of the shock. It's well smoothed out. But if we observe the entropy profile, we notice that only the physical artificial viscosity is able to predict the entropy overshoot, whereas the Laplacian model is giving an erroneous monotonic profile. The idea is that we want to design a shock capturing technique to simulate actually compressible turbulent flows. So we consider also a simple case of compressible isotropic turbulence, where the classical choices of the kinetic energy spectrum, Mach number, and Reynolds number is such that they lead to the natural development of shocklets in the flow field, which are localized, strong compression events. And once again, in this case, we want to study the impact of the shock capturing technique on kinetic energy transfers, essentially. So the best way to do that is just to monitor kinetic energy and vorticity, which are, of course, very important for turbulent flows. And we notice that, first of all, that without any artificial viscosity, the simulation fails pretty early. Instead, using the Laplacian model, we have a stable simulation, but extremely dissipative on vorticity modes. Whereas the physical model gives quite good results in terms of agreement with the reference DNS data. On the other hand, if we look at thermodynamic quantities, so in terms of temperature variance and dilatation variance, both models are quite dissipative, but still the physical model is way less dissipative than the Laplacian model. So in this first part of the presentation, we essentially compare two different types of artificial viscosities, the physical artificial viscosity based on a bulk viscosity, and a Laplacian artificial viscosity. In terms of entropy overshoot, the physical artificial viscosity was preserving this property of Euler's equations, whereas the Laplacian was not able to do that. In terms of vorticity and kinetic energy dissipation, the physical artificial viscosity was way less dissipative than the Laplacian model. Whereas in terms of temperature and dilatation dissipation, both models were quite dissipative, but still the physical model was way less dissipative than the Laplacian. So all of this information points out that the physical artificial viscosity are more suitable for the simulation of compressible turbulent flows. And for the rest of the presentation, we essentially use this kind of model for simulation of compressible turbulent flows. The second part of the presentation instead is focused on essentially classical spectral analysis techniques to quantify numerical dispersion and dissipation or diffusion of high-order meters. So it's quite well known that in turbulent flows, kinetic energy is generated at the larger scales, and then it cascades towards smaller and smaller scales. But of course, due to computational reasons, it's not always possible to solve all the scales involved in the problem. And within the framework of large AJS simulation, a certain amount of dissipation is usually injected at the smallest resolved length scale by the computational grid. There are many ways to prescribe this kind of dissipation. We can categorize essentially between two main categories, using implicit AJS and explicit AJS. The first, the former, uses the numerical dissipation of the scheme itself to mimic kinetic energy transfers, whereas explicit AJS are based on explicit dissipative models like eddy viscosity models. Both of them, they have their own pros and cons. Implicit AJS are computationally very cheap, because you don't need to implement any actual sub-bit scale model. And they are characterized by a mathematic under-resolution detection, in the sense that, for example, spectral element, discontinuous spectral element methods based on upwind numerical fluxes, they inject dissipation only if the flow is under-resolved. So they are essentially non-active for well-resolved features like laminar flows. But implicit AJS are usually strongly dependent on numerics. So different choices of order of approximation, numerical fluxes, and grid size can give completely different results. Explicit AJS instead are based on a well-established theory, which makes them a little bit more robust. But on the other hand, they have always been designed without taking into account at all the numerics. And this is not a great thing as well, that sometimes implementing the same SGS model on different schemes can lead to quite different results. So the idea is that, of course, both of them have their pros and cons, and we need to find some kind of combination of the two. And we'll talk about that later on. Right now, I will present, let's say, the numerical schemes that I used during my PhD and that we will study with eigenanalysis, which are spectral difference method, and the Flux reconstruction method, which are two types of discontinuous spectral element methods. They are based on a definition, spectral difference is based on a definition of two different set of points within the finite element, the solution points in the interior part, and the flux points, including also the extrema of the element. The solution is known as the solution points and is interpolated using Lagrangian polynomials defined on this set of points. In this way, the solution can be extrapolated on the flux points, including the extrema. At this point, the information coming from the left and right boundaries of a given interface is used to correct the flux at this location, and then it's possible to define another interpolation on a different set of points, on the flux points, interpolating the values of the flux in these locations. At this point, this interpolation is analytical. You can just apply the derivative and evaluate this term on the solution points to have the divergence of your flux. This flux reconstruction method is essentially the same, very similar. You have just the definition of one set of nodes, the solution points. Once again, the solution is known at its locations. You can extrapolate the value of the solution at the interfaces. But at this point, the flux computed, let's say, this time I will do this, computed on the solution location is corrected using the information coming from the interfaces in combination with analytical functions called correction functions. The idea of the correction functions is that they bring the information from the interface back in the interior part of the element. Different choices of correction functions, they give you different, let's say, types of flux reconstruction methods. The most popular ones is that you are able to recover a spectral difference scheme for linear equations and of a nodal discontinuous polarity. And these are the two variants that we will consider in the next few slides. Once again, this interpolation is analytical. You just apply the derivative, you evaluate on the solution points, and you have your divergence of the flux at these locations. So the idea is that we want to introduce spectral eigenanalysis to estimate numerical dispersion and dissipation. These analyses are usually based on the discretization of a linear directional equation using wave-like solutions. You discretize this system with your favorite high-order method, and you obtain essentially an eigenvalue problem where you link the spatial oscillation, spatial frequency theta, and temporal oscillation omega. So in the standard temporal eigenanalysis, you impose a value of theta, and you solve an eigenvalue problem in terms of omega. Of course, different schemes will give you different matrices H, and you will get different values of omega. The idea is that this is a standard temporal eigenanalysis because you are imposing a spatial oscillation, and you are studying how it evolves over time. So imposing theta, and you are evaluating omega. Then the real part of omega quantifies dispersive errors, which are essentially associated to the errors in estimating the propagation speed of these oscillations. And the imaginary part instead represents dissipative errors, and they quantify the errors in terms of magnitude of these quantities. For the standard spatial analysis, you can do essentially the same thing, but instead of imposing a value of theta, you impose a value of omega, and you solve a nonlinear equation in terms of theta. You can see that the problem is essentially flipped. So before we were imposing a spatial oscillation and study how it was evolving over time. Here we are focusing on imposing a temporal frequency and study how it behaves while propagating over space. So you can see that the first approach is more suitable for, let's say, periodic problems, and this for inlet-outlet kind of problems. Once again, you can obtain essentially very similar plots in terms of real part of theta and imaginary part of theta with more or less the same interpretation readapted in terms of space evolution of dispersive and dissipative errors, essentially. All these results can be quite easily generalized for non-constant directional velocities, where it's a very interesting problem because now we can find some differences between the flux reconstruction as the recovering scheme and the actual original spectral difference scheme. And it is quite well known that these two schemes behave very differently in terms of accuracy and stability. So we need more, let's say, classical eigenanalyses are very useful, very insightful, but for this particular problem, we need something more complex and more specific in order to distinguish these two schemes. And for this very first approach, we consider simple sinusoidal direction velocity to study the influence of non-constant direction velocities. We have, of course, like plenty of combinations that we can study in terms of numerical fluxes, order of approximations, type of analysis that I presented in these last few slides. Here we consider, just because it's the most relevant result, the case of hyper-upwind, so very strong upwind numerical fluxes, a fifth order approximation, and we monitor spatial dissipation. And we look at the different schemes, the flux reconstruction DJ, flux reconstruction SD, and the original spectral difference scheme. This problem is, or this combination, let's say, is characterized by the presence of what they're called dissipative bubbles, so that some frequencies are affected by numerical dissipation, and they're very close to frequencies which are not affected by numerical dissipation at all. And we want to essentially look at the evolution of these bubbles, increasing the level of inhomogeneity of the direction velocity. We are increasing the amplitude of the sinusoidal profile. And we can notice that for the flux reconstruction DG, more or less, these bubbles are keeping the same shape. They are a little bit enlarged. but instead using the Flux Reconstruction SD, these bubbles are also stretched along the horizontal direction, and this is even more evident for the spectral difference scheme. The idea is that you want these profiles to be as smooth as possible, because having these sharp interfaces between frequencies not dissipated and dissipated in actual nonlinear simulations can trigger kinetic energy transfers between frequencies, and it can affect the stability of the simulation. So we want to essentially test this kind of behavior, these differences between the spectral difference scheme and the Flux Reconstruction schemes for actual simulation, nonlinear simulation, and consider a simple Euler explanation of a spatially evolving turbulence. Once again, notice that we are considering a inlet-outlet kind of configuration to be coherent with the spatial eigenanalysis. In this case, we impose a simple oscillating inlet condition, and we consider two different grids, a homogeneous one and one with a sudden change of resolution. In this way, we expect to see spurious oscillations coming from the upper boundary and from the sudden change of resolution. I want to see how this oscillation they will change using different schemes and how they will behave. So we consider also two different Mach numbers, a small Mach number and a relatively high Mach number, and two different Riemann solvers, which are essentially numerical fluxes in discontinuous spectral methods, the rho solver and the Lux-ready flux. These choices are we took these choices because for relatively high Mach number, these Riemann solvers they behave both as upwind fluxes, but in the limit of small Mach number, the rho solver is still upwind, and the Lux-ready flux behaves as a hyper upwind flux. And this is the case that we want to study in connection with the theoretical analysis before. So we want to see the case of low Mach number and the Lux-ready flux. We compare a classical discontinuous polarity simulation and a spectral difference simulation, and we can notice that with the two different grids, we can notice that we do have oscillations coming from the upper boundary and a little bit smaller coming from the interface between the two resolutions. And we can notice still that these oscillations are much smaller with the spectral difference rather than with the classical discontinuous polarity. The possible explanation is that, well, first of all, the spectral difference scheme is in general more dissipated in terms of spatial eigenanalysis with respect to discontinuous polarity, but it's also interesting to see a possible explanation in the better distribution of dissipation along frequencies for this spectral difference with respect to the discontinuous polarity scheme. So in the second part of the presentation, we essentially listed the classical spectral eigenanalysis to estimate numerical dispersion and dissipation of high-order methods. These analyses are computationally very cheap, one-dimensional, very easy. They are also quite insightful. You can still noticing very relevant differences between discontinuous polarity and spectral difference various schemes. But sometimes they can be, of course, oversimplified, and a very easy example is this difference between Flux Reconstruction SD and SD. So we consider a very first generalization to non-constant vector velocities, where we notice quite important differences between the spectral difference dissipative curves and the Flux Reconstruction counterparts. And we essentially tested this behavior using numerical experiments of error equations, where we noticed that the spectral difference was characterized by much smaller oscillations than VG. Finally, the last part of the presentation will be focused on actual compressible turbulent flows. We'll consider a couple of airfoil flows and shockwave turbulence interaction in a compression expansion run, where all these things that I discussed will be simultaneously involved. So, since now we introduce the concept, let's say, of numerical dissipation, we can present the spectral element dynamic model, which is still, let's say, related to the whole concept of implicit and explicit AJS that I introduced before. In fact, the spectral aerodynamic model is just an eddy viscosity model, where the eddy viscosity is multiplied by a turbulent sensor, which resembles the idea of the shock sensor, and it's an activation function varying between 0 and 1 to distinguish between well-resolved and under-resolved features. To give you an idea of how it works, here we show the viscous dissipation of a classical Taylor-Green vortex test case with a relatively high order of approximation. It is quite well known that using implicit LES of this configuration, you have an overestimation of viscous dissipation. Instead, applying classical models like Smagorinsky, sometimes usually you have an underestimate of the viscous dissipation. The idea of a spectral element dynamic model, and in general, every dynamic model, is somehow to combine these two components and get the right fit for the reference filtered DNS. The idea of the spectral dynamic model is that when you increase the order of approximation, so you have a decrease of numerical dissipation, you are injecting more and more explicit dissipation, so that if numerical dissipation is enough to describe kinetic energy transfers, you're okay with that. If instead the decrease is way too much, you inject some explicit dissipation. So it's somehow a midway between implicit LES and explicit LES. In this few simulations that I will present, we want to study essentially the behavior of spectral dynamic model for more complex geometries and in general configurations. We consider a transition, the flow over a transitional airfoil, a limited Mach number, and a transonic airfoil for larger Reynolds numbers. The first case is essentially characterized by the natural development of a laminar separation bubble on the upper side of the airfoil, and predicting the dynamics of this bubble can be particularly challenging within the LES framework. In the second case, instead, the touch region is much more reduced, much more limited, but on the upper side, due to the transonic nature of the flow, you have the natural development of a shock wave, which causes the flow to separate right after. So in the first case, we are just interested in studying the behavior of the spectral dynamic model for more complex geometries. And of course, since we are almost in incompressible conditions, there's no need of artificial viscosity. In the second case, instead, we want exactly to study the interaction between these two models being simultaneously active for this configuration. In terms of the transitional airfoil, we have obtained quite good results in terms of wall coefficients, like the friction coefficient and wall pressure, and also in terms of the size of the laminar separation bubble, both, let's say, qualitatively and also quantitatively, with respect to the most refined simulation of this problem by Garman and Wiesbaum, which gives results which are quite good agreement with our simulation, with way less degrees of freedom. What is actually interesting is that we also considered identical implicit LES of this configuration, and since we used a 6th order and 8th order simulation, both simulations, they were unstable. And once again, this reflects what I said before, that implicit LES, sometimes for relatively high order of approximation, are not really reliable, and they can be, of course, they can be unstable since you have a very small amount of numerical dissipation. But what we're interested in is to study, essentially, to understand the behavior of the turbulent sensor in general of the SGS model for this configuration. So we show here a snapshot of the flow field and the turbulent sensor applied to it. Of course, we have a huge activation in the separated region, but what's more interesting is that the model is able to identify the shear layer as a mildly unresolved feature, and there's no activation at all in the laminar separation, in the laminar region, which means that the spectral dynamic model is able to successfully detect under resolution and able to be inactive in these regions of the flow field. We can do essentially the same thing for the transonic airfoil, where we notice once again that the model is essentially active in the wake and inactive in the laminar part of the flow, which gives again that there's a good under-resolution detection. And as a new thing, it's interesting to notice that it's inactive close to the shock, meaning that the bulk artificial viscosity is enough to regularize the shock, and there's no need of additional shear viscosity, so or eddy viscosity. So in the first part of this presentation regarding the airfoils, we studied these different zones of activation of the turbulent sensor, so that is inactive laminar regions and more fully turbulent regions. Now we focus our attention on the, let's say, the activation of the artificial viscosity. When we consider the simple model sensor that I introduced at the very first slides, we notice that there's a huge activation in the wake, of course, because from numerically speaking, it's detected as under-resolved, this feature. And we had to correct using some kind of physical correction known as the Niccolò sensor, where you compare the essentially the divergence and the vorticity of the velocity field in such a way that if these terms are more or less of the same order of magnitude, the sensor is active. But if we are in vertical regions, where we have negligible effects of compressibility, it tends to zero and it deactivates the sensor. Finally, also the numerator has been modified in order to be active only for compressions. And of course, we have a way reduced activation in this wake region, and only in the wake region with more or less the same activation close to the shock wave, which is ideal. Of course, in this way, you can reduce the dilatation dissipation, which was one of the main drawbacks of bulk artificial viscosities. And you have some good features in terms of CFL restriction, because of course, if you have large values of viscosity very close to the wall where the grid is very small, you can be forced to have very, very small stable time steps, which are essentially useless because you don't need any artificial viscosity in this region. So as one last slide on the airfoil simulation, we are showing the average viscosity and average artificial viscosity, showing once again that the viscosity is only mildly active close to the shock and takes the biggest values, of course, in the wake region. And the artificial viscosity instead is active close to the shock and almost zero in the wake. So that the two models are acting on two different regions of the flow field as expected by the physics of this problem. So, for this part of airfoil simulations, we essentially use this to study the spectral dynamic model for more complex configuration, geometries, and we use a transonic airfoil test case to study the interaction between the spectral dynamic model and the artificial viscosity, which were active in different regions. So there was no eddy viscosity at the shock location, and no artificial viscosity in vertical regions, which is ideal and is connected to the problem that we consider here. Now, I will take a step here. In the previous transonic airfoil test case, we already point out that essentially shockwave and turbulence were quite well separated one another. Now we want to study a problem where they strongly interact the two aspects of turbulence and shockwave. So we consider a quite well-known popular test case of turbulent boundary layer interacting with a shockwave generated by a compression ramp. So that we have shock waves, so the artificial viscosity will be active, strongly interacting with a fully turbulent boundary layer, and everything within the high orbit stabilization. So here we have all the ingredients that I explained in the previous part of the presentation, and they will all interact one another. The classical geometry of this problem has been slightly modified. We added an expansion corner to study the effect of strong expansions on turbulent structure, as we will see later on. The inlet condition has been imposed using plain digital filter, and the physical and numerical details about the simulation have been chosen in order to match the direct numerical simulation by Priebe and Martin. The Reynolds number based on the momentum thickness is small enough to have a well-resolved direct numerical simulation with a relatively small number of degrees of freedom, only 54 million. So in the first part, we consider essentially, again, a few of coefficients to compare with other simulations. We have quite good agreement with the other references, where we have some slight differences in the upstream region, since most of the other simulations use different techniques to prescribe the turbulent boundary layer. The simulation by Wu and Martin was based on a recycling rescaling technique, and the simulation by Zhu and others on a blow and suction transition to turbulence, which is a much more expensive technique, but it's expected to be more representative of the transition to turbulence. In this sense, we have a much better agreement in terms of wall pressure with respect to the DNS by Zhu rather than the one by Wu and Martin. And finally, we have pretty good agreement in terms of size of the separation bubble with respect to the experimental data by Riget and others. On a secondary note, we want once again to reiterate the activation of the artificial viscosity at the correct regions. It's mostly active close to the main shock, whereas it takes quite small values close to the compression ramp. And this is very important because it's also from a physical point of view, it's well known that this region is characterized by strongly compressible small-scale oscillations, and excessive dilation dissipation in this region would give a completely different kind of physics. But what we are actually interested in this setup is to study essentially kinetic energy transfers under more compressible conditions. So this is the classical, well, for somebody who works on LES, is the classical balance of filtered kinetic energy. And we will focus our attention on the pressure dilatation work, which essentially links the resolved kinetic energy balance and internal energy balance, and the subgrid scale dissipation term, which links resolved and unresolved scales, unresolved kinetic energy. Where if it's less than 0, you have forward scatter, so that the unresolved scales, they act as a sink of resolved kinetic energy, and vice versa. If it's bigger than 0, you have back scatter events, so that the unresolved scales, they act as a source of resolved kinetic energy. It's important to highlight that based on the definition of the overlying operator, you can both have filtering and averaging, so that you have direct connection with AJS and runs approaches. So that the equations will be exactly the same. We will just change the nomenclature so that you have always resolved kinetic energy, unresolved kinetic energy, and SGS tensor versus average kinetic energy, fluctuating kinetic energy, or turbulent kinetic energy, and Reynolds stresses. But the equations will be exactly the same. So we have this parallelism between averaging and filtering for the remaining part of the presentation. So first part, we started studying the average kinetic energy across the interaction. So we plotted here all the terms in the balance along the streamwise direction. And we can notice, well, first of all, that all these terms, they sum up to 0, meaning that we are able to close the kinetic energy balance, and all the relevant scales of the problem were resolved. And secondly, we can notice, of course, that most of the kinetic energy transfers, on average, they happen close to the main shock, where you have a strong compression. Of course, kinetic energy is transformed into thermal energy, and strong forward scatter events, so that the average kinetic energy is transformed in turbulent kinetic energy in this region. In terms of kinetic energy transfers, if we look at the SGS dissipation in the whole domain, we can notice, well, once again, that we have some forward scatter negative values across the interaction, and back scatter close to the expansion corner. So that close to the interaction, you have a generation of turbulent kinetic energy, and a dissipation close to the expansion corner. So this result is a little bit odd, because it's usually on average it's very difficult to observe backscatter events, but it's also true that the classical kinetic energy cascade is supposed to hold on average and in compressible conditions. So you can already understand that this backscatter event is more or less is mainly associated to the role played by compressibility. In this term, we want to, once again, we want to study the interaction between kinetic energy transfers and compressibility. So we want to find some kind of relation between these two terms in the kinetic energy balance. So we computed the joint probability density function between these two terms over space, both in terms of average field and filtered fields. And we can notice that, well, once again, we have a large amount of backscatter in the second quadrant of the first plot, so that we have positive values of K3 for expansions, so positive values of K1. And in terms of, instead, watching at the full joint probability density function, we can notice that there's some kind of correlation between these two terms, so that compressions are more likely to experience the classical forward scatter events, and expansions backscatter events. We want to dig a little bit deeper in this sense, and we want to understand it. This is, of course, like, again, how much is related to the compressibility effects. So we decompose the SGS dissipation in a deviatoric and a spherical component. The deviatoric is representative of incompressible motions, and the spherical is more intrinsically compressible. So that if we compare only the K3 term with the sum, only the deviatoric part, so K3 plus lambda, we can observe that all the backscatter that we first observed now completely disappears. And this makes sense with what I said before, that the incompressible part of the motions, they still respect classical kinetic energy cascade, and the fluctuating flow field, the compressible part of the fluctuating flow field, is only dissipative on the average velocity, so that on the average kinetic energy more than velocity, so that this part can be modeled with usual inequality models and so on, whereas the spherical part is causing both backscatter and forward scatter, and more complex models needs to be taken into account for this term. So, once again, now we want to study the interaction between the relation between pressure dilatation work and only the deviatoric part of SGS dissipation. And we can notice that, as I said before in the previous slide, all the backscatter that was in the second quadrant now disappears, becomes classical forward scatter events. And there's essentially no correlation between these two quantities, whereas instead, in terms of filtered fields, we still see some mild correlation. And this is quite interesting, meaning that on average, it's the kinetic energy cascade is satisfied, it's always negative, there's no correlation at all between compressions, expansion, general pressure dilatation work, and kinetic energy transfers, whereas on in filtered sense, you still have some correlation, so that SGS models will be significantly different with respect to, let's say, RANS models for these kind of configurations. So this last part of the presentation, we consider a classical compression expansion ramp, highly accurate DNS of this setup using our spectral difference code. First of all, we notice once again that the artificial viscosity was mostly active around the main shock, thanks to the Duclos sensor. And then we consider a series of a priori analyses based on explicit filtering and averaging of the flow field. We notice a correlation between pressure dilatation and SGS dissipation, which on average was only caused by the spherical part, so that the deviatoric part instead was was only caused by the spherical part, whereas on filtering sense there was still some mild correlation between these two terms. In terms of a big, large summary of very dense on the presentation of today, the first part was dedicated to the bulk artificial viscosity, which was able to preserve the entropy overshoot across an ambitious shock and was very low dissipative in terms of vorticity kinetic energy. The second part was focused on spectral analysis of high-order meters, where we presented a generalization for non-constant advection velocities, where we noticed some relevant differences between spectral difference and a set of Flux reconstruction schemes. And finally, the last part was focused on compressible turbulent flows. In the airfoil simulation, we observed that the spectral dynamic model and artificial viscosity were active on different regions as expected, whereas in the compression expansion ramp, we studied kinetic energy transfers under more compressible conditions. observing a correlation between pressure dilatation and SPS dissipation. The dilatoric part was causing, at least on average, only direct energy cascade, so can be modeled with classical eddy viscosities. And the spherical part instead was causing both back scatter and forward scatter, so that more complex models are needed. Each of these topics are currently undergoing further developments. The artificial viscosity, we are working on a better dynamic activation based on exponential moving averaging. In terms of spectral analysis, we are working on a fully discrete analysis, taking into account also time integration errors. Actually, this part is already made. We just uploaded an archive paper on the matter. And finally, we have plenty of ideas on how to use essentially the DNS data from the compressible turbulent flow part, starting from a better, again, under-resolution detection, maybe using characteristic variables, which are more suitable for compressible flows, in the development of ad hoc subgrid scale models based on a separation between, of course, the dilatoric and spherical part, the dilatoric with classical eddy viscosity model, so spectral element dynamic model, for example, and the spherical part maybe using some kind of bulk term. And finally, we will perform a series of deeper a posteriori LES studies focused on the role of data compressibility and in general the numerics, so different orders, different grids, different numerical fluxes. Thank you for your attention. Also from the online audience. Yeah, everything was crystal clear. Wonderful.
I have just one curiosity, if you can add something more on the computational cost, like number of degrees of freedom with respect to other securitization techniques.
This is something that actually, like, to be pretty honest, didn't care that much with my PhD, meaning that, I mean, most of my job was more about the modeling and the different kind of models that we implemented. It's well known that, let's say, spectral discontinuous spectral methods are more or less comparable, let's say, in terms of computational cost. And also, let's say, the classical compact finite differences, which is essentially the main, let's say, other scheme to compressible flows is more or less comparable with discontinuous finite elements. And the only thing that is relevant, let's say, in terms of computational cost is that the artificial viscosity only based on the bulk viscosity, since it's only based on that term, usually have big values, and the time step restrictions are more important with our model rather than a Laplacian model or limiters and so on. But of course, you know, you gain a little, you lose a little.
Yes, so there are not, let's say, some specific problems or some specific issues that you need to take into account for the resolution of the final algebraic system of equations, like special type of preconditioners or something like that.
Well, also that in these terms, like in at least in my cases, we always use explicit time integration. So on this matter, like there's not much information, at least in my case. Let's say there's not much in terms of there is a lot in the literature about preconditioning of compressible Navier-Stokes equations, but not for the work I did in my PhD.
So you only regard explicit time integrations.
Yeah. And also in this sense, also the fully discrete analysis that I did for obvious reasons, we mostly focus our attention on explicit schemes because of, let's say, it was more useful for us, essentially. That's it. Are there other questions?